Section 6.1 is random variables, and this is the only section that we're going to be covering tonight because this is a foundational topic for us that's going to lay the foundation for what we can expect in the future. We're going to revisit a few topics that we have seen before, such as discrete and continuous variables. Objective 1 is to distinguish between discrete and continuous random variables, but first we're going to get a definition of what a random variable is. If we roll a fair die, the possible outcomes are numbers 1, 2, 3, 4, 5, and 6. And each of these numbers has a probability of 1/6, because if it's a fair die, you have an equally likely chance of rolling any one of the 6 numbers. The outcome of this experiment is called a random variable. The numbers that we roll are called the random variable. A random variable is a numerical outcome of a probability experiment. Some of our experiments will yield either discrete or continuous random variables, so we need to revisit what the difference is between discrete and continuous data. Do y'all remember? One of these is countably many. That's the discrete, where you can enumerate the items that you have. For example, the number that comes up on a roll of a die is discrete. The number of siblings a randomly chosen person has, that's discrete, because you can't have a fraction of a child or a fraction of a number on a roll of a dice. It is that number. On the other hand, a continuous random variable consists of things that can be measured on a continuum. So if I were to give you two numbers, for example 2 and 5, on a continuous random variable, if this is the range of values, you could have an infinite number of values in between these two numbers that your random variable could assume. But if I use the numbers 2 and 5 for the discrete data, you could only have a 2, a 3, a 4, or a 5. But here I could have any number in between 2 and 5 carried out to any level of decimal places. Even if I'm talking shoe sizes, which come in half sizes, there's still only a finite number of shoe sizes between a size 2 and a size 5. Now I'm talking about kids' shoes because adults don't come that small. Objective 2 is to determine a probability distribution for a discrete random variable. We've seen something that looks similar to this when we talked about probability in Chapter 4. These were the two conditions we said that had to be satisfied for a probability, where this right here was our sample space. We said the probability of our sample space had to be equal to 1. Well, in a probability distribution for discrete data, you have these individual probabilities assigned to random variables, and the sum of all of these has to be equal to 1. In this example problem, I want you to decide if each of the following is a probability distribution. The way that you look at these tables is the top row here represents your random variable. It's a numerical value that's assigned or paired with a probability. These two conditions have to be satisfied. Probabilities can only have a value between 0 and 1, and the sum of all the probabilities has to be equal to 1. We've looked at this capital sigma before, haven't we? It means to add up everything. Is this a probability distribution? You're shaking your head no. Why not? It doesn't add up to 1, but also it has a negative probability. We can't have negative probabilities. What about this next one? Is this a probability? All of these probability values are between 0 and 1, so that first condition is fine, but is the second condition satisfied? Yes, this is a probability distribution because all of these probabilities add up to 1. 0.17, 0.25, 0.31. If I were to add all these numbers up, I would get 1. What about this next one? Is this a probability distribution? No, why not? I have a probability that's bigger than 1, so clearly both of these things fail. In this example, we're told that 4 patients have made appointments to have their blood pressure checked at a clinic. Let X be the number of them that have high blood pressure. Out of the 4 patients that have made appointments, we want to let X be the number of patients that have high blood pressure. It's possible none of those 4 patients have high blood pressure. It's possible exactly 1 of them have high blood pressure, 2 of them have high pressure, 3 of them have high blood pressure, or all 4 of them could have high blood pressure. Here's the probability that none of the patients have high blood pressure. This is the probability that exactly 1. Do you see how to read the table? So the first part of this question says to find the probability that either 2 or 3 of the patients have high blood pressure. Do you remember early on when we started discussing probabilities, if we saw the word or between probabilities, what did we do to those probabilities? Or means add. And if you don't know that, you need to add that to your formula sheets. When you see the word or, that means to add the probabilities together. So the probability of 2 or 3 of the patients having high blood pressure is going to be equal to the probability that 2 of them have high blood pressure, which is 0.27, just looking at the table right here, plus the probability that 3 of them have high blood pressure. And what do I put for the probability of 3? 0.08. And when I add these two numbers together, I get, so this means that there's a 0.35 probability or a 35% chance that 2 or 3 of the patients who made appointments for that day will have high blood pressure. Part B says find the probability that more than one of the patients have high blood pressure. More than one means we're looking at what for X? 2 is more than 1, 3 is more than 1, and 4 is more than 1. So that's going to give us 0.27 plus 0.08 plus 0.01, and that is 0.36. So adding that one more patient didn't change things a whole lot. On part C, we see the words at least one. What did I tell you to do when you see the words at least one? The reason we use the complement is because the probability of an event is equal to 1 minus the probability of the complement. There's a whole bunch of different ways that we could get at least one of these patients. I could have exactly one, and it could be the first patient, second patient, third patient, fourth patient, or I could have 2, and you see the problem with that. We went over an example like this in, I think it was section 5.3 lecture video. I may be off on that section number, but I think that's right. So how we began is we identify what is our complement. What is the complement of at least one? None of the patients have high blood pressure. The probability of the complement of the event is equal to the probability of 0. And what is the probability of 0? This is the number for x for our random variable. If x is 0, p of x is 0.23. So now I go back to this thing right here. This 0.23 is what gets plugged in right here in the formula. So the probability that at least one has high blood pressure is going to be equal to 1 minus the probability that none of them have high blood pressure, and that's going to be 1 minus 0.23. And what is 1 minus 0.23? 0.77. Objective 3 is to describe the connection between probability distributions and populations. Statisticians are interested in studying samples drawn from populations. Random variables are important because when an item is drawn from a population, the value observed is the value of a random variable. The probability distribution of the random variables tells how frequently we can expect each of the possible values of the random variable to turn up in the sample space. We're going to actually make a probability distribution for the information that's presented in this table. For our probability distribution, we need to have a random variable and a probability associated with that random variable. We were told in the problem that the random variable represents the hourly parking fee. So that's what x is equal to, but it has to be a number. So starting with the cheapest parking space available, what would that be? $1.50, and then what? $2, $4, and then $4.50. Now we need to find a probability associated with each one of these. Remember, we said that the probability of an event is equal to the number of elements in that event divided by the number of elements in the sample space. This is our basic definition of probabilities. This is why we do chapter 4 before we do this. What is our sample space for this problem? 1,000 parking spaces. The number of elements in our sample space is always going to be equal to 1,000. So to get the probability for the places that cost $1.50 per hour, we look and see how many places we have. So the number of elements in this event would be 423 divided by 1,000. When you put this into your calculator, you end up with 0.423. Actually, there's no need to put it in your calculator. If you're dividing by 1,000, that means you need 3 decimal places in your number. So that's 0.423. For the $2 parking places, what would be the probability? So 142 are covered long-term spaces that cost $2 per hour, so this would be 142 divided by 1,000, and that's 0.142. And what would be the probability of being charged $4 an hour? It's 57 divided by 1,000, and you're right, that's 0.057. And then how would I calculate the probability of being charged $4.50 per parking place? Perfect. Generally on your probability distribution, you will only see what I have written in red. What I have in blue is how I came up with those probabilities. This table is what we call the probability distribution. Objective 4 is to construct a probability histogram for a discrete random variable. I don't remember, but I'm pretty sure I did not ask you to do this on the homework, but it's important that you know how to read them, and we've already discussed histograms earlier in the semester. We learned that we could use histograms to summarize data in a sample. So for our discrete data, we would put our numbers down here along the horizontal axis. The height of the bars would be the probability. Do you notice something noteworthy about the shape of this distribution? It's normal. It's symmetric and bell-shaped. In Chapter 7, this is going to become very important to us. Objective 5 is to compute the mean of a discrete random variable. Recall that the mean is a measure of the center. So the mean of a random variable provides a measure of center for the probability distribution of a random variable. For this distribution, the mean would be somewhere around 2.5 because that's where the middle of the distribution is. If you're calculating the mean by hand, this is the formula that you would use. It's just the sum of the product x times p of x. And if you have a very few number of random variables, it's worth knowing how to use this formula. But if you have a lot of random variables and probabilities in your table, and by a lot I mean more than 3 or 4, I'm going to show you another way to do this on your calculator that also works for standard deviations and variances. But we're going to do this one by hand. A computer monitor is composed of a very large number of points of light called pixels. It is not uncommon for a few of these pixels to be defective. Let x represent the number of defective pixels on a randomly chosen monitor. The probability distribution of x is as follows. Find the mean number of defective pixels. We use this symbol right here for the mean, and then we use the x to show that it's the mean for our random variable x for our discrete data. That's going to be equal to the sum of the product x times p of x. So I take each one of these pairs x times p of x, and I multiply. The first x is 0 times p of x, 0.2. Then the capital sigma means I add, so I'm adding to that x. The next x is 1 times the p of x associated with that. It's 0.5 plus 2 times what? 0.2 plus 3 times 0.1. The arithmetic is easy enough that I think we can handle this one without going to the calculator. This is going to be equal to 0 plus 0.5 plus 0.4 plus 0.3. And when we add this up, what do we get? 1.2. 5 and 4 is 9 and 3 is 12. With one decimal place, that makes it 1.2. Another word for the mean is the expected value. There are many occasions on which people want to predict how much they are likely to gain or lose if they make a certain decision or take a certain action. Often this is done by computing the mean of a random variable. In such situations, the mean is sometimes called the expected value and is denoted by E of x. If the expected value is positive, it's an expected gain. If it's negative, it's an expected loss. You will see the words mean and an expected value used interchangeably. Mean is synonymous with expected value. That means the mean of your random variable is equal to E of x, the expected value. In this example, we're told that a mineral economist estimated that a particular venture had a probability of 0.4 of a $30 million loss, a probability of 0.5 of a $20 million profit, a probability of 0.1 of a $40 million profit. Let x represent the profit. Find the possible distribution of the profit and the expected value of the profit. Does this venture represent an expected gain or an expected loss? The first thing we have to do is set up a probability distribution table. In order to do that, I need to know what x and P of X are for all possible outcomes. These probabilities have to total up to 1. What's the first thing that I'm told in this problem that would tell me what a random variable and a probability is? There's a probability of 0.4, and what would X be if the probability is 0.4? I'm not going to write out the millions, I'm just going to put 30. Now, is that a profit or a loss? If it's a loss, another way of saying a loss is a negative profit. This is actually negative 30 because it's a loss. There's a 0.4 chance of a $30 million loss. And if you lose money, that's not a profit, it's a negative. Then there's a 0.5 probability of what? What will X be for the 0.5 probability? 20. Is it positive or negative? Positive because it's a profit. Negative when it's a loss. All right, and then the last probability, we've got to have one more because this doesn't yet add up to 1. It's 0.9, so I need a 0.1. What has a probability of 0.1? A $40 million profit, so that's going to be positive. The losses are negative, the profits are positive. So that's why this negative is right here on the 30, because it's a loss. So we did the first part of this. We found our probability distribution. This is your probability distribution right here. Now we've got to find the expected value. Remember, the expected value is the mean, and the expected value, we said, is equal to the sum of the product x times p of x. So for each of these three random variables, my expected value is going to be what times what? Negative 30 times 0.4 plus times plus 40 times 0.1. Alright, so that would be negative 12 plus 10 and then plus 4. So that would be equal to 2. So what I would say here is that I can expect a $2 million profit. Like I said, this isn't overly taxing using this formula if you only have a few of these random variables. If you have more, it can get a bit taxing, or if you need to do the variance and standard deviation. This is not something that I want to do by hand. I'm going to show you how to use the calculator and not these formulas here. But what I do want to point out is that the variance and standard deviations are measures of spread. The bigger the standard deviation and variance are, the more spread out your data values will be. The smaller they are, the more closely clumped together your data values will be. The mean measures the middle of the data. Standard deviation and variance tell you how spread out your data values are. The variance is represented by this symbol right here. That's the population variance. The standard deviation is the square root of the variance. Or you could say the variance is the square of the standard deviation. Either way works. Means the same thing. I told you I'm not going to teach you how to use these formulas because they can get a little tedious. And we already have the TI calculator, and it's this pre-programmed into your calculator. We just have to know how to access it. So let's look at the steps. These are the steps for finding the mean and the standard deviation on the TI calculator. We have to do a little more work to get the variance, but our calculator will give us the mean and the standard deviation. Your first step will be to put your x's in list 1. Do y'all remember how to put data into a list in your calculator? We hit stat, enter, enter. Your next step will be to put your p of x's in list 2. After you do that, you want to go to the home screen. How do we go to the home screen? Second mode. Hopefully you're starting to memorize some of these now. After you do that, you're going to hit stat, and this is a button, so I'll put it in a box. You're going to go over to calculate, and you're going to go down to your one variable stats. Actually, you don't have to go down to anything because it's the first thing on your calculator, and then you're just going to hit enter to access it. Once you do that, it's going to bring up a screen on your calculator that asks you for the list. That has to be list 1. And then it's going to give you an option to fill in the frequency list, and that needs to be list 2 in order for this to work. And then you're going to calculate. And we're going to look at an example of this in just a minute. If you have the older TI calculator, the older operating system, this will be your step 4. It's going to look exactly the same, but then you've got to do something different. You're going to have to do stat, calc, enter, and that's going to pop the one variable stats up on your home screen. Then you're going to have to hit second 1, comma, second 2. What this puts on your home screen is list 1, comma, list 2. It puts that on your home screen. Then you hit enter and it'll give you everything else. Here's the nice, pretty publisher produced steps, but I don't think they're as thorough as the steps that I give you with the keystrokes. So let's go back to the data that we had earlier. What's the first thing that I do? Plug the data into my calculator. So I'm going to hit stat, enter. List 1 is going to be 0, 1, 2, 3. And then I move over to list 2 and I hit 0.2, 0.5, 0.2, and 0.1. Once you have your data in your calculator, what do you need to do? Go to the home screen, second mode. Then what? Stat, calc, enter. List 1 is fine for my list. Then you move your cursor down to frequency list. List 1 was already populated, but my calculator doesn't have anything in the frequency list. I need list 2 to be there. How do I put list 2 there? What do I hit? Second 2. And then I go down to calculate and hit enter. This is the mean that we got earlier, isn't it? That 1.2. This number right here now is the standard deviation. This 0.8718. This is the output that we got. The mean is this value right here. And this number right here is the standard deviation. What would you do if I asked you for the variance? Because the variance isn't one of the outputs that we get. What do we know about the variance? I didn't ask you to find the variance here, but we're going to find it anyway just so I can take you through the process of how you find the variance on the calculator. The variance is the square of the standard deviation. The variance is sigma squared. The standard deviation is sigma. If I were to hit 0.8717 squared, let's show you what happens. So if I were to round this standard deviation to say 4 decimal places, I would get 0.8718. 0.8718. And if I just square this number, this is close to what the variance is, but it's not quite right because there's some rounding that went on. If you want to get the exact value of the variance, and if it's a homework problem, rest assured that's going to want the exact value, very precise. You don't want any rounding going on. So does that mean you just type in all those numbers? No, because that's even rounded. It's just they quit displaying numbers after a while. In order to get the variance accurately, you see this button right here that says VARS? VARS stands for variables. If you hit that button, then there's an option that says statistics. We hit 5 for statistics, and then number 4 here is the standard deviation that we saw in our output right here underneath the S of X. My pointer is not really showing up very well, but I'm pointing right here. This number right here is this value right here. So I want to select that so that it pops it up on my home screen. That's what I square by hitting the X square button, and if I hit enter, I get the exact value, not a rounded value. Do you see the difference between the two numbers? It's close, but not exactly the same. So the way that we would get the variance on our calculator, you first have to do the one variable stats. And those steps were the steps above. Then you're going to hit VARS 5 to get the statistics. Then you're going to hit 4 to get the standard deviation. And then you're going to hit X squared. That's the X square button on your calculator. And then you're going to hit enter. That's how you would find the variance on your calculator.